So here I'm gonna demonstrate how I build my VPC, and we have three virtual machines inside it and four subnetworks. And each of the interface of a virtual machine was assigned a private IP, and one of the private IP was associated with the public IP, which is I get from the AWS, and yeah, these two subnetworks are subnetwork 3 and subnetwork 4 are dedicated to server and client, and we can SSH from my own desktop to these two virtual machines through this subnetwork using the public IP that AWS provided. And now this is the server terminal, and I'm gonna ping the outside world from this terminal. Yeah, it works. And I'm gonna ping the VivaOS ETH0. And this is our client terminal. So I did the same thing. Yeah, we can ping to the Google DNS server, and then we're gonna ping the ETH1 interface of VivaOS router.
So since my almost every virtual machines are lost forever in my previous experiment, so I just create this new network with specified almost every interfaces with new IP addresses. So here is my so this is my client, and this is my server. I'm gonna turn on the TCP dump and keep listening the incoming packet with the protocol ICMP. And on the client, I'm gonna ping my my server. And oh, sorry, this is a trace route. Yeah, I'm gonna ping my route. Yeah, so here, as you can see, yeah, it works.
I'm sorry, I just forgot to show how the traffic is actually routed through the router. So this is my router, this is the client, and the left one is my server. So I'm gonna turn on the TCP dump on this port, and also on this port, the ETH0. I'm gonna ping from my client along this way to the server, and we can see the packet is captured by the TCP dump on this port, and as well on this port. So I'm gonna turn on start listening from EH1 on the router, and ETH0 listening to any incoming ICMP packet. Okay, they're both started, and I'm gonna ping to the IP address of my server. Yeah, see? So now the packet is actually going from here to here and then to here. And I would like to add some details here. As you can see here in this line, this is actually a ping request sent from this IP address, which is actually the IP address of my client, and the destination is this 133, which is the IP address of my server. And also the reply packet is actually going through my router, and this is the reply. And yeah, that's it. So now I've done the bandwidth measurement experiment using the iPerf3 tool. This is the bandwidth of the client. It shows that yeah, it took 10 seconds to send all of the UDP datagrams, and the overall bandwidth is 1.2 gigabits per second. And let's move to here. This is the client. Sorry, this is the server, and the bandwidth is 1.19 gigabits per second, and it's a little bit lower than what shows in here. I think the reason is that the time, the server thought that he had received all of the UDP datagram is this long time, but in reality, the client took 10 seconds to send all of the UDP datagrams. So this is the main reason that caused the drop of the bandwidth on the server side. So this is the bandwidth test with the TCP protocol. So as you can see, the TCP bandwidth is a little bit lower than the UDP bandwidth, but we don't have the lost packets here, as you can see. After adding this line of code, both the server and the client, we got here the server side bandwidth dropped much more than before. I think the reason is because the delay that we set is actually influencing the ending time of this test. So the server thought the time increased, and so with more time increased, the bandwidth would drop more significantly. So I think this is the reason. I can feel lag after setting the delay to be 1 second, and the result here proves my point, that the bandwidth drops significantly as we increase the delay. So after we set the delay to be 0 and then set the loss to be 10%, and the result we've got shows that there are many datagrams are dropped. So as you can see, there are 32% of data are lost. So the bandwidth also dropped. I don't know why, but there's nothing change on that kernel blocks was I was trying to run it on the background. So now I've set up the queuing strategy to be TBF, which stands for the token buffet filter, and also the output rate to be 100 million bits. And as we can see here, the result, almost every packets are lost. So, and you can see here the received rate here is almost 100 million bits per second, but the sending is much more than that. I got this arrow operation not supported when I was trying to modify the speed of the interface. I think well, the reason we couldn't do that is because the machine is actually located on the AWS cloud. So maybe the user, we are not authorized to modify the hardware after we left the first stage, like the hardware configuration at the beginning.